Alright, now we're going to look at the applications of momentum and impulse from first principle. But just before we start, I'm going to use it's a real life story to really lay emphasis on momentum and impulse. I think long time ago when I was, 17 years, long time ago when I was 17 years old, we took a road trip to Limpopo. And on our way back, it was during the Easter time. On our way back, we saw a billboard written, don't drink and drive, or adhere to the speed limit because speed kills. And ever since then, I was inquisitive to think if speed kills, it means, have you ever realized the speed of an ant or the speed of a normal fly? They move at a speed in the ranges of 240 meters per second. And most of the time, or ebusweni. So if real speed kills, why are we not dead now? Then I realized that the advert could have said momentum kills, not speed kills. Something will kill you if it possesses a high velocity and a high mass. So if something has a lighter velocity, it won't kill you. Because why? It does not have enough momentum to do so. But for you to have enough momentum to kill something or to be more powerful, you have to have more mass and velocity. But nonetheless, let's approach these questions with that story in mind. The question says, calculate the momentum of the car with a mass of 2,400 kg, moving with a velocity of 3 meters per second to the right. So I'm going to do these two questions for you so that you follow the algorithm. Now let's do it. I said we define momentum by a small p, and we say momentum is the product of mass and velocity. What is the mass of the car? It's 2,400 kg. 2,400. Then we multiply. What's the velocity? The velocity is 3 meters per second. Good. Now what's the answer? 7,200 kg meters per second. Now I will have to emphasize something here. We simply substituted there because if you look at the unit measurement for the mass, our mass was given in terms of kilograms. So they correspond to the System International. And then if you look at the velocity was given in terms of meters per second. If the velocity is given in terms of meters per second and the mass is given in kg, you don't have to convert it. But suppose if the mass was given in terms of grams, you're going to convert it to kilograms first. Do you guys understand? So in a nutshell, the mass should always be in kilograms, the velocity should always be in meters per second. Now let's go to the second question. The second question says, a 0.5 kg tennis ball moving with a velocity of 20 meters per second. It hits back at a velocity of 30 meters per second. Question is, calculate the exerted force on the tennis ball if the time of contact was 0.2 seconds. Let's imagine. Suppose I'm having a tennis ball. This tennis ball is moving with a velocity of 20 meters per second. So I'm hitting this tennis ball against the wall. Now they say this tennis ball hit back with a velocity of 30 meters per second. If the time of contact between the wall and the tennis was 0.2 seconds, we need to calculate what we call the exerted force. Now here is the application of impulse. You can see that is impulse. You want impulse. But the definition of the impulse is not that simple definition of impulse being the change in momentum. But the definition of the impulse will be the second definition that I've given you. Impulse being the product of force and period. We are going to do exactly that. Now I'm going to say impulse is equals to F net times delta t, right? This is still impulse. Now, here I said we still have the same ball, that we didn't change the balls, meaning that ball has the mass of the ball is constant. So my impulse will be caused by the change in velocity because it bounced back. And we have seen that the velocity changed from 20 to 20 meters per second. Are we okay with that? Now we are going to say to what is positive, to what it's positive, to what is positive. To what, when it bounces back, the velocity will be negative. Towards is positive. When it bounces back, the velocity will be negative. Because velocity is a vector. So we denote the direction of the velocity using the sign. Positive is it goes towards the wall. When it bounces back, its velocity will be negative. Meaning, if you take that denotion, this velocity of 20 meters per second will be positive because it goes towards, and the one that it hits back with will be negative because velocity is a vector. Now let's move. So we agree that the change in momentum will be caused by the change in velocity. We agree. So we are saying mass is constant. Mass is constant. We all agree. Mass is constant. So we have V final minus V initial. Good. Now we have F net delta T. Can you then allow me to divide by delta T so that I have F net? No, let me divide by delta T. I divide by delta T. So I have F net. Can I write this F net this side and the rest that other side? Good. Now I have F net is equals to M Vf minus V initial delta T. The mass of the ball was 0.5. This mass is okay because it's given in kilograms. So the mass is okay. Now the velocity, what's the velocity final? We said towards is positive. If it goes this way, positive. When it bounces back, it will be negative. The velocity final will be the velocity at which the ball is returning. Do we all agree? We are saying this way. This velocity, it says it hits with the velocity of 20 meters per second. That velocity is the initial velocity, but it's positive because it's pointing towards the wall. The velocity that the ball returns with will be negative in this case. Do you all agree, guys? Good. Now, my final velocity will be negative 30. Negative 30. Negative 30. Negative 30. Do you all agree why? Guys, do you all understand why? Look, the ball is going towards the wall with a velocity of 20 meters per second. It hits back with a velocity of 30 meters per second. Right? We are saying towards is positive, right? Away from the wall is negative. So the velocity final is away from the wall. Away from the wall, so the velocity will be negative. That is why we have negative 30 there. So I'm going to have minus here. This minus comes from this. 20. So I have minus 20 there. Divided by delta t. Delta, what is my delta t? My delta t is 0.2. 0.2. So I have 0.5 minus 50. So on top I have negative 25. Negative 25. Negative 25 divided by 0.2. What's my answer? Negative? Negative 125. Right? But I'm going to write my, let me denote my answer. This negative speaks to the direction. This negative speaks to the direction. So my answer will be 125 newtons. Good, let's analyze it. According to Newton 3. Well, according to Newton 3, I have to indicate direction. This negative speaks to the direction. Now, according to Newton 3, the ball hits the wall. The ball hits the ball. And the force that the ball is exerting to the wall is in this way. Suppose this is my wall. Suppose this is my wall. The ball comes and hits the ball. And the force that is being applied, by the tennis to the wall is this way. Right? Now, we said this direction is negative, right? So the wall is going to apply the force in which direction? This way. Let's make sense of our answer. Do you all guys understand why our answer is negative? Right? So we are saying this direction is positive, it's towards the wall. Suppose it hits the ball. This direction is positive. This one towards the wall is positive, away from the ball is negative. Right? Now, the ball is going to exert the force. A positive force in this case because it's going this way. Right? According to Newton 3, the wall is going to respond with a force. What will be the direction of that force? This way. That's why our answer will be negative. So you can just say here 125 newtons towards the ball. Towards the ball. Do you all understand, guys? Good. Any other questions? Any other questions? No. Good. Now let's proceed. I'm going to talk about two types of interaction when we look at the conservation of momentum. Two types of interactions. After those two kinds of interaction, we're going to strictly deal with two types of collisions. After that, we're going to do the consolidated exercise. Now, let's move forward. Remember, when we stated the conservation of momentum, we said the total linear momentum of a closed system remains constant in both magnitude and direction. And you understood the definition weight by weight, the principle weight by weight. Good. Now, we have two types of interaction. Can I rub here? We have two types of interaction. When we were talking about the principle of conservation of momentum, we spoke about the system. We said the total linear momentum of the system. And the system comes as a result of interaction. When two objects interact, then we have a system. When I'm modeling a tennis ball, if the tennis ball bounces back, I'm not getting a system there. The best thing that I can get is the impulse, because we have one tennis ball. But immediately when the tennis ball interacts with another ball, we're going to have a system of two objects. Do you guys understand? Now, when two objects interact, they can interact in two forms. When we're looking at the principle of conservation of momentum, one interaction will be coupling. I'll make a typical example. Suppose a car collides with a truck. A car collides with a truck, right? Now, after collision, we have a car, it collides with a truck. Because the truck has a higher mass than the car, they'll collide, douche. After colliding, they'll both move with the same velocity, following the direction of the truck. It makes sense why they follow the direction of the truck. Because the truck has higher mass than the car. Do you all understand? Good. That type of interaction is called coupling. They've interacted. But that type of interaction is called coupling. Because after the interaction, after that collision, what happens? They move together with the same velocity. Now mathematically, this is how we denote that form of coupling. This is how we denote that form of coupling. The principle of conservation of momentum says, I have that plus that. This is initial. This is mass of object 1, mass of object 2, initial velocity of object 2, initial velocity of object 1. Good. Now it says we have that object 1, V final, plus object 2, V final. It says that, right? This is how we denote the principle of conservation of momentum, mathematically. Now, coupling, it will come in a sense that we have this before. They come. What do I mean by this? This is the mass of object 1, initial velocity of object 1, the mass of object 2, initial velocity of object 2. But I said after interaction, what then happens is they move together with the same velocity. They move together with the same velocity. Then what happens? Is that you add their masses. You have mass 1 plus mass 2. Then they move together with the same velocity. You're going to have VF there. Please write it's coupling. Then you have the second form of interaction. You have a car and a car. Suppose you have a car and a car, a blue car and a red car. They collide. After colliding, they move again in separate direction. We call that type of interaction. Combustion interaction. They combust after interacting. Now, it will be denoted by this form. So this will be combustion interaction, this will be coupling. Let me explain again. Under combustion interaction is that you have mass, object 1 coming with its own mass, it comes with its own velocity. Let's picture it. We have object 1, they haven't interacted. Do you see them? They haven't interacted. So object 1 comes with its own mass and its own velocity. Right? Object 2 comes with its own mass and its velocity. After interaction, let's look at this experiment. It's very important. This experiment, after interaction, they come. After interacting, they move separately. Now, do you see that object 1 still has a different velocity than object interacting at? Can you see that? The velocity of object 1, even after interaction, is not the same as the velocity of object 2, even after interaction. I'll repeat the experiment. You have the red car. Maybe Chippy owns the car, the red car. Natasha owns the blue car. Then they come together, they collide. Initially, let's model them initially. Initially, Chippy is moving with his own velocity, and the car of Chippy has its own mass. Now, we look at the car of Natasha. The car of Natasha has its own mass, and it has its own velocity. They come, they interact. After interacting, they just collide. After colliding, they combust. So we see Natasha still has a unique velocity from Chippy's velocity, and Natasha still retains his or her own mass. When you look at Chippy still retains the latter as well. Chippy still retains his velocity, and Chippy still retains the mass as well. That form of interaction is called combustion interaction. Can you all relate? Now, a typical mistake made by many students. I said velocity is a vector. This is a tip that I'm giving you. When you are given a question of conservation of momentum, you need to draw the diagram. Let's make a simple calculation. We have Chippy, the car of Chippy, we have Chippy's car. We have Chippy's car. Right. Now, here we have Natasha's car. Good. Now, Chippy, actually this car goes this way. It goes this way. Initial velocity of Natasha, of Chippy. Initial velocity of Chippy, let's say it's 2 meters per second towards this direction. Towards this direction. Towards this direction. This is my left. So it goes towards this direction. I'll denote it by this form. The mass of the car is, let's say, 2,400 kg. You have Natasha. The initial velocity of Natasha, let's say, is 3 meters per second. The mass of the car, let's say, is 2,000 kilograms. The question then is, Chippy collides with Natasha. Calculate the final velocity of Chippy-Natasha system. The reason why I'm saying Chippy-Natasha system, I'm referring to the interaction of both the cars. Because I said what makes a system is when two objects interact. And our objects are Chippy's car and Natasha's car. Right? Velocity is a vector. Let me answer this. They say calculate the final velocity of Chippy and Natasha system after they've collided. But the examiner has to specify what happens after collision. Now I'm telling you that after collision, they'll couple and move together with the same velocity. In this situation, I'm telling you that they'll collide. After colliding, they'll move together with the same velocity. My question is therefore calculate the final velocity after that collision. Now, I'm saying velocity is a vector system. You have to denote direction by either plus or minus. So we are going to choose this direction as positive. Right? Chippy is going this way, Natasha is going this way. But we are choosing this direction as positive. So I'm going to have the mass of Chippy, initial velocity of Chippy, plus the mass of Natasha, initial velocity of Natasha. I'm told that after collision, they'll couple and move with a uniform velocity. Calculate that velocity. So I'm going to have VF. There's no need for me to specify that VF because it belongs to both the cars. Now I have the mass of Chippy plus the mass of Natasha. Now the mass of Chippy, let's look at the mass of Chippy. The mass of Chippy is 2,400 kg. Initial velocity, I'm saying we choose this direction as positive. So I can put positive 2 plus the mass of Natasha. The mass of Natasha is 2,000 kg. But the initial velocity of Natasha moves this way. But I'm saying my positive is this way. It means my negative is this way. So I have negative 3. Guys, do you all understand? So I have VF, I don't know VF. The mass of Chippy is 2,000. The mass of Chippy is what? It's 2.4. 2.4. The mass of Natasha is 2,000. Right? Now I'm going to have this. I'm going to have 4.8. Here I'm going to have negative 6,000. Now I'm going to have V final 4.4. Good? Now here I'm going to have 1.2. I'm going to have 1.2. I'm going to have VF 4.4. Now I'm going to divide because I want to solve for VF. I'm dividing by 4.4. I'm dividing by 4.4. Now this cancels this. I'm having 1 as my VF. Remember, I have a negative here, negative 1.2. So I'm having 1 as my VF. Negative 0.27. Meaning, generally, we said this direction is positive. This direction is positive. And we are getting a negative answer. It means the final velocity of Natasha Chippy system is this direction. Meaning Natasha, after they've collided, they'll move in which direction? In this direction. Because we're getting a negative answer. Now let's conclude our answer. Our answer will then be VF is equals to 0.27 meters per second. I said this is my left. This is my left, it will go towards my right. Any questions? Any questions? Any questions? Now let me highlight important things here. Here you have to note types of interactions, either combustion or coupling. Secondary to that, you have to treat velocity as a vector. Many students treat velocity as a scalar. If you treat velocity as a scalar, you'll have a plus and a plus here. And already you have a disaster. So if you treat velocity as a vector, velocity, it has both magnitude and direction. And in terms of calculations, we denote direction as either plus or negative. Do you guys understand? Lidikaya, I see a question there. Can you speak loud so that everyone hears?
Why don't you not have kg meters per second?
As my unit of measurement. Now, according to my dimensional analysis here, let's look at dimensional. The question is, why don't I have kg meters per second as my units of measurement? Look, I said we have coupling here. So I have mass plus mass 1, mass 2 is equals to VF. Right? Here we are going to have mass, the total mass. Here we are going to have VF. The unit measurement of this mass is mass. The unit measurement of VF is meters per second. But in this case, we want VF. So that's why we dissociated meters for meters per second. The unit, let me correct my statement. The unit measurement of mass is kg. So here you have kg. You understand, because it's mass. So you have kg. Now, because we are interested in just velocity, the unit measurement of velocity is meters per second. Do you understand? Good. Any other questions? We are going to do a question